Imagine for a second that you are the architect of a brand new universe.
Okay, I like where this is going.
Right. But you don't just get to build the buildings and the roads. You have to actually invent the fundamental laws of physics.
Wow. So like from the ground up.
Exactly. From the very bottom. You have to decide how objects interact, how they share information, and crucially, how they keep secrets from one another.
That's a huge responsibility.
It really is. And welcome to today's deep dive. If you're joining us, and we are absolutely thrilled you are here, you are about to step into the shoes of a software architect.
It's a fun pair of shoes to wear, honestly.
It is. So our mission today, tailored specifically for you, the learner, is to explore an MIT lecture that introduces programming in Java.
Right, the MIT Intro to Programming and Java Source. It's a classic.
It really is. We're going to demystify exactly how computer code organizes, protects, and stores information. I mean, we'll start with the tiniest, most localized variables and scale all the way up to those massive, incredibly flexible data structures that power the modern web.
Yeah, and to do that effectively, we have to look really closely at the rules of the road, because code isn't magic.
Right, as much as it feels like it sometimes.
Yeah, no, it does. But it's actually a series of strict, sometimes painfully literal instructions. When you grasp just how literal a computer actually is, you start to understand the hidden architecture of, the entire digital world around you.
To kick things off, the source material gives us this brilliant look at what happens when those literal rules get crossed. There's a code snippet in this MIT lecture that results in a digital baby being left endlessly hungry.
Oh, the baby example, it's so good.
It's so funny, but also understanding that specific, almost comical coding error provides the foundational logic for preventing things like credit card fraud in global software systems.
That sounds wild, right? It seems like a massive leap from a hungry digital baby to preventing financial ruin.
Yeah, a huge leap.
But the connection lies in one really critical concept, which is memory management. Before any piece of software can securely manage millions of users, it first has to prove it can manage memory inside one single, simple object.
Okay, so let's look at the actual code from the MIT lecture. The source outlines a baby class, so we are creating a digital baby.
Right, a virtual infant.
And this baby object has a variable called servings, which represents, how much food it has eaten so far.
Makes sense.
Then there's an action the baby can take, a method called feed. The feed method takes in a number of new servings that you want to give the baby.
So you're handing the program an input, like a specific amount of food.
Right. But inside the feed method, the code is written exactly like this. It says, servings equals servings plus servings.
Yep.
And when I read that in the source, it honestly stopped me in my tracks. If I tell a computer, servings equals servings plus servings, how does it know which servings I'm talking about?
That is the big question.
Right. Am I talking about the baby's total stomach capacity, or am I talking about the new spoonful of food I just handed it? It feels like having two people named servings in the exact same room, giving an instruction to the room, and just expecting the right person to answer.
Yeah, it's a terrible naming convention.
So why would a programmer ever use the same name twice and risk that kind of confusion?
Well, I mean, in a small program, they probably wouldn't. They just name everything uniquely, like new servings and total servings.
Right, that's what I would do.
But at a massive scale, with millions of lines of code, programmers inevitably run out of good names. Or, multiple teams will use the same common terms like count or total, or in this case, servings.
No, so they just bump into each other.
Exactly. And the computer handles this repetition through a foundational rule called scope.
Scope. Like a field of vision.
Yeah, that's a great way to put it. Consider a block of code as a closed room. Variables only exist, they can only be seen by the computer within their local room. So when the computer enters the feed room, you hand it a temporary variable called servings, representing the new food.
The spoonful.
Right. Now, the baby object itself also has a permanent variable attached to it, completely outside that room, which is also called servings.
The stomach.
Yes, the stomach. Because the computer is hyper-literal and, frankly, exceptionally lazy, when it reads servings equals servings plus servings, it simply grabs the closest, most temporary variable inside the room.
Wait, so the computer takes the new spoonful of food, adds it to the new spoonful of food, and completely ignores the baby's actual stomach.
That's exactly what it does. The baby's total servings never increase. The local input variable shadows or blocks the computer from seeing the baby's permanent memory.
Because the baby stays hungry forever. That's tragic.
It is. It's a digital tragedy. But to fix this, the source material introduces a specific keyword. You change the code to say this.servings is 0, this.servings plus servings.
Ah, this. So by adding this with a period, you're changing the computer's field of vision.
Exactly.
Mm-hmm.
You're forcing it to look outside that temporary room. The key word, this tells the computer, hey, do not use the temporary variable here. Look at this specific object's permanent memory.
So you're taking the temporary servings and adding it to the object's permanent servings.
Yes, you're giving the literal mind of the computer a very specific pointing finger.
I love that. And I have to mention a really great detail from the lecture. Once the baby is successfully fed using this servings, they include a poop method.
Naturally, you have to.
Of course. And it just prints out all better to the system and immediately resets the this.servings variable back to 0.
Which is funny, but it also illustrates control over state perfectly.
Right.
The object state changes over time based on very strict rules. But this actually leads us to a much darker application of scope and access.
From baby poop to the dark side.
Exactly. Because understanding who can see a variable and who can change it is the absolute cornerstone of software security.
Right. And the lecture transitions from the baby to a class called malicious.
Yes, the malicious class.
And this piece of code acts like a digital pickpocket. The source shows a malicious method that takes in a credit card object. And inside this method, it simply says card.expenses equals 0.
Which is terrifying.
And then, just to add insult to injury, it prints out the card.card number for everyone to see.
I mean, the ability to wipe out a credit card balance with one line of code is effortlessly devastating.
But that's what I don't get. If I can just write a malicious class that sets my credit card expenses to 0, why is the global banking system still functioning? Why is it so easy in this MIT example?
Well, the malicious code only works in that specific example because the programmer of the credit card class made a catastrophic error.
Oh, they messed up.
Big time. They left the expenses variable public by default, meaning anyone, anywhere in the program can just reach in and change it.
Wow. So they just left the front door open.
Exactly.
Yeah.
To solve this, the text points to a different class called scope review, which defines a variable as private in var3.
Okay, private.
Yeah, the word private is a strict impenetrable shield in Java.
But let's play this out because I have a question here. Let's say we put the word private in front of our credit card balance. It's completely private and only the credit card object itself can see or touch it.
Yeah.
How does an actual legitimate bank teller update my balance when I make a deposit? Because they are outside the object, right?
That is the core of object-oriented design right there. Think of a private variable as cash locked inside a massive steel vault.
Okay, I'm picturing the vault.
The bank teller cannot just walk into the vault and put the money on the shelf themselves. The object holds the only key. Instead, the programmer creates specific controlled windows.
Oh, like those little teller windows with the thick glass?
Yes, exactly. In Java, these are called getter and setter methods.
So the teller passes a message through the window.
Right. The teller hands the deposit to a method called, say, make deposit. That method is actually part of the vault.
Oh, okay.
So it checks the teller's credentials, it verifies the amount isn't negative, and then the method itself turns around and updates the private balance inside the vault.
Oh, wow. So the external world can never touch the raw data directly.
Never. Programming is often taught as the art of creating things, but in reality, it's just as much about hiding data and severely restricting access.
That's a wild shift in perspective. Okay, so we have these beautifully constructed steel vaults. We have credit cards locked down with private variables.
Right.
But if I'm building a massive piece of software, like an operating system or a global online store, I'm going to have thousands of these little secure classes.
Oh, easily tens of thousands.
Right. So how do we organize them without creating utter chaos?
Well, organization is the next necessary layer of architecture. Because if everything is secure but scattered randomly, the system is basically unusable.
Yeah, you'd never find anything.
Exactly. So the lecture solves this by introducing packages.
Packages. The source describes packages as directories, basically folders on your computer desktop.
Yeah, that's exactly what they are. Classes in the same package are bundled together logically because they serve a similar purpose.
Oh.
The MIT lecture uses a package called parent tools. And inside parent tools, you place your baby class and maybe, a baby food class.
Right.
Then you have a totally separate package called adult, which holds the parent class.
It's like the aisles in a grocery store.
Oh, I like that.
The baby aisle has all the baby items. The adult aisle has the adult items.
That's it.
But what happens if two different software companies make a product with the exact same name?
Okay, where are you going with this?
Well, say I'm building a massive program and I need a class called a list. And I have two different external libraries I'm pulling from, and both have a class named list.
How does the computer know which one I want?
Ah, packages are designed specifically to solve that exact problem. We call it naming collision.
Naming collision. Makes sense.
Yeah, the source material explicitly highlights this. Packages allow you to separate similar names by defining their path.
Like giving them a last name.
Exactly like that. They give the example of shopping list versus packing list.
Because they live in different folders, the computer treats them as entirely different tools, even though the class itself is just called list.
Okay, so you just specify the path, but honestly, typing out shopping list every single time I want to use it throughout a massive file sounds exhausting.
It would be. And Java actually anticipates that fatigue, which is why it uses the import statement.
Okay.
If you want to use the baby class inside the parent class, you just declare at the very top of your file, import parenttools.baby.
So you're making an announcement at the top.
Yes, you're telling the compiler, hey, for the rest of this file, when I say baby, I mean the one from the parent tools folder. You must import everything you need from outside your current package.
Wait, really? Do I literally have to import every single tool I use? Because that seems like a massive amount of administrative overhead just to get started.
Mostly, yes. But there is one foundational exception highlighted in the text.
Oh, thank goodness.
All classes, automatically, without any import statements, see everything inside a specific package called java.lang.
Java.long, so language basics, essentially?
Precisely. It holds the fundamental building blocks of the Java language. Things like text handlers, the string class, or system, which is what lets you print messages to the console, like our all better baby message.
Oh.
The creators of Java knew you'd use these in almost every single file, so they made java.long universally visible. You don't have to ask permission to use the basic fabric of the universe.
I love that, the basic fabric of the universe. Okay, so we have our classes scoped locally so they don't confuse their own memory. We have our variables locked in vaults as private. And we have everything neatly organized into package aisles.
Check in.
Now let's talk about the actual items inside the aisles, the data. The lecture transitions from these structural concepts into the real powerhouse of the language, the Java API.
Yes, we're moving from organizing classes to organizing the information those classes hold.
Right.
Historically, if a programmer wanted to store multiple items, say a collection of 10 books, they had to use an array.
Oh, the lecture provides the syntax for this. It's books equals new book 10. And just reading the text, this method looks incredibly tedious.
Oh, it is. It really is.
Because you have to declare the exact size of your list before you even start. You are explicitly carving out 10 slots.
Yeah.
If you suddenly get an 11th book, the program just crashes.
Pretty much. And the text notes, you even have to manually create an integer called next index just to keep track of where the next empty slot is.
Ugh, manually adding one to it every single time you store a book.
Exactly. It forces the programmer to micromanage the hardware. Arrays are incredibly fast, don't get me wrong, because they're a single, continuous block of physical memory. But they're completely unforgiving.
So they're rigid.
Extremely rigid. And that rigidity is why the lecture introduces the array list.
Ah, the upgrade.
A major upgrade. Part of the Java API, the array list, handles all that micromanagement for you. You never tell it how many items you are storing, and you definitely don't track a next index.
Oh, you just throw things into it.
You just command it to add a book, and the array list dynamically accommodates it.
But wait. You just said physical memory in a computer has to be a specific carved-out size. How can an array list just magically stretch its memory?
Oh, it doesn't. It's a brilliant illusion.
An illusion? What do you mean?
Under the hood, an array list is just an array.
No way.
Yeah. When you create an array list, it secretly carves out a small, hidden array, let's say 10 slots. You add items until it fills up.
Okay, so what happens on item 11?
When you try to add the 11th item, the array list hits pause. Behind the scenes, it creates a brand new separate array that is double the size of 20 slots.
Oh, wow.
Then it copies all your existing books over to the new array, places the 11th book in the next open slot, and then quietly destroys the original smaller array.
That is wild. It does all that manual labor, like moving the boxes to a bigger warehouse, in a fraction of a millisecond without ever bothering the human programmer.
Exactly. It frees the human to think about the logic, not the plumbing.
Okay, I love array lists now. But sometimes you need a collection with stricter rules, right? The lecture introduces another structure called sets.
Right. Sets are fascinating.
The defining rule of a set is uniqueness. To me, a set acts like a bouncer at a very exclusive club.
A bouncer. Okay, let's hear it.
You walk up to the door, the bouncer checks the clipboard. If you're already on the list, the bouncer just nods, and you don't get added to the VIP list a second time. There is only one copy of each object allowed.
That is a perfect analogy. A set fundamentally rejects duplicates, and the text highlights two distinct types of sets, actually.
Oh, right.
The tree set takes the extra time to keep everything automatically sorted from lowest to highest.
Okay, alphabetical or numerical.
Exactly. But then there's the hash set, which doesn't care about order at all. It's pseudo-random, but it is blazingly fast at checking if someone is already on the list.
But what makes the hash set so fast? Like, why doesn't it have to read through every single name on the clipboard to see if I'm already there?
Because it uses a process called hashing. Imagine a complex mathematical function. You feed your name into this function, and it instantly spits out a highly specific, unique integer. That integer corresponds to an exact slot in memory.
Okay, so it's like walking into a massive parking garage, and instead of driving up and down every single aisle looking for your car,
Right.
your parking ticket performs a math equation that tells you your car is exactly in spot 4022, and you just walk directly to it.
Yes, you bypass the search entirely. It's instantaneous retrieval, which actually brings us to the grand finale of data structures in the lecture.
Maps.
Maps. So while a list or a set holds single items, a map stores pairs, a key and a value.
Exactly. You provide the map with the key, and it instantly hands you back the connected value.
The lecture uses an address book as the example, mapping names to specific MIT email addresses. So Evan, Eugene, and Adam are the keys.
Yep.
You feed the map the string, Eugene, and it uses that same hashing math on the name Eugene to instantly jump to the memory slot holding his specific email address, email2@mit.edu. And, it's important to remember, these aren't just abstract academic concepts.
Right. They're everywhere.
Everywhere. These structures, lists, sets, and maps are the literal gears turning beneath the glass of your phone screen.
Oh, absolutely.
When your digital shopping cart expands as you shop, it is acting like an array list. When a music app prevents you from adding the exact same song to a playlist twice, it's using the logic of a set and your contact list. That's a map.
That is so cool to think about. It's literally the fabric of our daily digital lives. But, these tools are incredibly powerful, but the source text ends with a very serious section titled Warnings.
Oh, yes, the warnings. You have to pay attention to those.
Definitely. The API handles the heavy lifting, but it demands you play by its rules. The warning states that if you use tree structures, the ones that sort things lowest to highest, you must read about the comparable interface.
Yeah, an interface in Java is essentially a legally binding contract for your code.
A contract.
Think about it. The computer already knows how to sort basic text or simple numbers. A comes before B, 1 comes before 2.
Sure.
But if you invent a brand new object, like our baby class, and you put 10 babies into a tree set, the computer panics.
Because it doesn't know how to sort babies.
Exactly. The comparable interface is a contract where your class promises, hey, I have written a specific method that explains exactly how to compare me to another baby based on age, or maybe servings eaten.
Okay, that makes total sense. And the second warning says if you use hash structures, you absolutely must read about the equals and hash code methods.
Oh, sure.
You have to mathematically define for the computer what makes two of your custom objects identical so it doesn't accidentally put them in the same parking spot.
You have to teach the machine your specific definition of equality, because it won't just guess.
Which honestly brings our journey completely full circle.
It really does.
We started by exploring the localized scope of a digital baby, learning how variables shadow each other if we aren't incredibly specific. Then we saw how leaving a variable public lets a malicious program completely wipe out a credit card, which taught us to lock down access with the private vault.
Yes.
We organized those vaults into neatly separated packages. And finally, we explored the Java API, moving from the rigid micromanagement of arrays to the dynamic, abstract power of array lists, sets, and maps.
It really is a profound shift in how a programmer operates. You move from counting individual memory slots to trusting massive abstract systems to do the organizing for you.
Which leads to a fascinating implication, I think. As software engineering has evolved, we've built taller and taller towers of abstraction.
Oh, for sure.
We started with micromanaging memory, and now we rely on these massive APIs where the computer handles all the heavy lifting in the background. And as we build increasingly advanced systems moving from basic Java apps to sprawling cloud architectures or, artificial intelligence, we are relying entirely on layers built by thousands of programmers before us.
It's true. I mean, most software developers today rarely have to worry about exactly how much physical RAM a single variable consumes. They simply trust that the array lists and the hash maps will just stretch and sort flawlessly behind the scenes.
But when something fundamentally breaks deep down in that foundational layer, how many people still understand the actual physics of the digital world well enough to fix it?
That's a scary thought.
Right. If we become architects who only know how to arrange the rooms, but we forget how to mix the concrete, what happens when the foundation cracks? It is a stark reminder that no matter how advanced our tools become, the strict, literal rules of the metal underneath still govern everything we build.
And, going back to that final warning in the text, it leaves us with something really profound to ponder.
Oh.
The source explicitly noted that defining equals in hash code only matters for new classes you build, right? Not the built-in Java types.
Right, because Java already knows what a string or an integer is.
Exactly. So what does this all mean for us? When you create a totally new object in software, say a massively complex digital representation of a human being, how exactly do you teach a computer what makes two complex objects equal?
Oh, wow.
Yeah,
Yeah.
like a deeply philosophical question hiding right there in a technical warning.
That is an incredible thought to leave on. Thank you so much for joining us on this deep dive. And for you, the learner, keep exploring, keep questioning the foundation, and we will see you next time.